This is NGC 6946, a spiral galaxy about 20 million light-years away. It is spinning. Pick a radius, measure how fast things orbit there, and put the answer on a graph. Then walk the radius outwards. And this is what Newtonian gravity predicts. If the mass of the galaxy is exactly the mass you can see, it should fall off, the way the planets do. Look at what that difference means. Same star, same distance from the center. Red is the speed Newton allows you. Blue is the speed we actually measure. That gap is not experimental error. The galaxy behaves as though it weighs 100 times more than the light it emits. The exam walks you the whole way, from a single hydrogen atom, to weighing an entire galaxy, to asking whether Newton's law itself needs fixing. Part A. We start with the smallest thing in the problem. First, the Bohr model. 3 short parts, 1 continuous chain. All of the mechanics is one line. The Coulomb force is the centripetal force. Solve for V. That is part 1. Before going further, do what a theorist always does and collect that pile of constants into one dimensionless number. Alpha. About 1 over 137. Bohr adds exactly one assumption. Angular momentum comes in units of h-bar. Substitute V, square both sides. One factor of r cancels, and the radii grow like n squared. And that is worth seeing. The allowed orbits are not evenly spaced. 1, 4, 9. Total energy is kinetic plus Coulomb potential. The kinetic term is exactly half the size of the potential one. That is the virial theorem for an inverse square force. Minus 13.6 electron volts. Notice the shape of it. The binding energy of hydrogen is just the electron's rest energy, times alpha squared, over 2. Now the part that turns this atom into an instrument. Change seats. Sit on the electron instead. From there, the proton is the thing going round, and a moving positive charge on a circle is a current loop. The equivalent current is 1 charge per orbital period, and the field at the center of a circular loop. That is A4. The electron's own magnetic moment sits in that field. Aligned or anti-aligned, the energies differ, and the level splits. The splitting is smaller than the binding energy by alpha squared. The hyperfine one is smaller again by the electron to proton mass ratio. 21 centimeters, 1.42 gigahertz. Any one atom emits this maybe once in 10 million years. But the universe has a great deal of hydrogen, so the signal is loud enough to hear across a galaxy. We have just built a ruler. The rest of the problem is about using it. Part B. From a rotation curve to a mass. One theorem does most of the work. For a spherical distribution, only the mass inside radius are poles on something at r. Everything outside, added up, pulls with exactly 0. For a circular orbit, the centripetal acceleration equals the field. This little formula carries the rest of the problem. Ca B.2, B.3. Get the bulge mass $mb$ from the Keplerian curve, then the rotation curve of a halo with $\rho m equals cm/ r m2 plus r2 $. Read the red curve at 10 kiloparsecs, about 20 kilometers per second. That gives a bulge of 900 million solar masses. And here is what the sky actually says. The points do not fall off. They stay flat, all the way out to where there are almost no stars left. So try a halo whose density falls like 1 over r squared. Integrate it. Gauss, then circular orbits, and out comes the rotation curve. Inside the core, expand the arctangent. The speed rises linearly, like a rigid body. Far out, the arctangent saturates at π/2, that term dies, and the speed goes to a constant. A flat curve, exactly as observed. This is everything the telescope sees. And this is what has to be there for the curve to come out flat. It does not shine, absorb, or reflect. It only pulls. We call it dark matter, which is a name that admits we do not know what it is. Part C. Now do it for our own galaxy, from a seed inside it. The Sun orbits the center at 220 kilometers per second. We look out along some direction, at an angle L from the center. A hydrogen cloud out there moves at the same speed, but on a circle of a different radius. Different projection onto our line of sight. Which means the Doppler shift is telling us the radius. Both objects share a speed, so the difference of the two projections depends only on the ratio of radii. Invert it. This is the whole mapping instrument. Point the dish, and the 21-centimeter line comes back with 3 peaks. 3 clouds along one line of sight. Each peak is a velocity, each velocity is a radius, and each radius is a circle on the map. Now sweep L through every direction. That is how the spiral arms of the Milky Way were mapped, without ever stepping outside it. Part D. There were 2 ways out of the problem. We took the first. Here is the second. Measure hundreds of spiral galaxies. Plot the total mass against the flat rotation speed, both on a log scale. They fall on a line. That is the Tully-Fisher relation, and its slope is about 3.75. So, does the dark halo model reproduce that slope? From Part B, both the flat speed and the mass are set by the same constant. Eliminate it, and the halo model predicts an exponent of 2. Draw that on the same axis. It is not close. A simple dark halo does not reproduce Tully-Fisher. Now the other road. What if there is no missing mass, and instead Newton's second law is wrong when accelerations get extremely small? And the accelerations out at the edge of NGC 6946 really are extremely small, about 10 to the minus 10, 11 orders of magnitude below gravity at the Earth's surface. In that regime, mu is just x, so the force law becomes m a squared over a naught. Put a circular orbit into it. And look what happens. The r squared cancels on both sides. The radius drops out of the problem completely. An exponent of 4. Put that on the plot next to the measured 3.75. A flat rotation curve is no longer something you have to arrange. It falls out of the law. And the constant and naught that comes out of the Tully-Fisher data is the same acceleration we measured at the edge of the galaxy. That is not nothing. So the exam hands you 2 consistent stories. Add matter nobody has ever detected, or change a law that has worked for 300 years. It scores both, and it declares neither the winner. All of it starting from 1 photon, 21 centimeters long, that a hydrogen atom emits about once every 10 million years.